Imagine a place where gravity is so intense, so utterly overwhelming, that nothing, not even light, can escape its grasp. A region of absolute darkness, a cosmic abyss. This is a black hole. For decades, they were relegated to the realm of science fiction. But today, we know they are very real, and they play a crucial role in the universe. Welcome to a journey into the heart of a black hole, where we'll explore their mind-bending properties, their origins, and the profound questions they pose about the nature of reality itself. Get ready to have your mind blown. In this video, we'll cover what exactly is a black hole, how they're formed, the different types that exist, what would happen if you fell into one, spoiler alert, it's not great, and what we're still trying to learn about these fascinating cosmic objects. Let's start with the basics. At its core, a black hole is an incredibly dense region of spacetime with gravity so strong that nothing, not even electromagnetic radiation like light, can escape from within it. It sounds simple, but the implications are profound. Think of spacetime as a fabric. Massive objects cause this fabric to warp. The more massive the object, the greater the distortion. With a black hole, the warping becomes infinite, creating a bottomless pit. The area from which escape is impossible is called the event horizon. It's the point of no return. The event horizon isn't a physical barrier. It's a boundary defined by gravity. Once you cross it, you're doomed. At the very center of a black hole lies the singularity. The singularity is a point of infinite density, where all the black hole's mass is concentrated. Our current understanding of physics breaks down at the singularity. It's a place where the known laws of the universe cease to apply. Pretty mind-boggling, right? So, how do these gravitational monsters come into existence? The most common way is through the death of a massive star. Stars are locked in a constant battle between gravity, which tries to crush them, and nuclear fusion, which generates outward pressure. This fusion process converts hydrogen into helium, and then helium into progressively heavier elements. However, when a massive star, let's say at least 8 times the mass of our Sun, exhausts its nuclear fuel, fusion stops. Without the outward pressure of fusion, gravity wins. The star's core collapses catastrophically in a fraction of a second, triggering a supernova, a colossal explosion that briefly outshines entire galaxies. If the remaining core is massive enough, typically more than about 3 times the mass of the Sun, gravity overwhelms all other forces. It collapses into a black hole. It's a truly dramatic end to a stellar life. But stellar collapse isn't the only way black holes can form. There are other, more exotic possibilities. Scientists theorize about primordial black holes that might have formed in the very early universe, during the Big Bang, due to extreme density fluctuations. These could be much smaller than stellar mass black holes, potentially even microscopic. We haven't directly detected any yet, but they remain a fascinating area of research. Black holes come in a range of sizes, each with its own unique characteristics and effects on the universe. The primary types we recognize are stellar mass, intermediate mass, and supermassive. Stellar mass black holes are the most common, typically ranging from about 3 to dozens of times the mass of our Sun. As we discussed, they form from the collapse of massive stars. Our Milky Way galaxy is estimated to contain millions of these stellar mass black holes. When these black holes are in a binary system with another star, they can become visible. The black hole pulls matter from its companion, forming a swirling accretion disk around it. As the matter spirals inward, it heats up to millions of degrees, emitting intense X-rays that we can detect. Then we have intermediate mass black holes, IMBHs. These are the Goldilocks of the black hole world. Not too small, not too big. Ranging from about 100 to 100,000 solar masses, they're harder to find, and their formation is still a bit of a mystery. Some theories suggest they form from the mergers of smaller black holes or in dense star clusters. Finally, we have the giants, supermassive black holes, SMBHs. These behemoths reside at the centers of most galaxies, and they can be millions or even billions of times more massive than our Sun. The supermassive black hole at the center of our Milky Way, Sagittarius A star, pronounced Sagittarius A star, is about 4 million solar masses. The Event Horizon Telescope gave us our first-ever image of Sagittarius A star, confirming its existence and providing invaluable data for understanding these galactic anchors. These SMBHs play a crucial role in galaxy evolution, influencing the formation of stars and shaping the overall structure of their host galaxies. When actively feeding, they can power incredibly luminous objects called quasars, which are among the brightest objects in the universe. Okay, let's address the burning question. What would happen if you were unfortunate enough to fall into a black hole? The answer is not pretty. This is where things get really weird, and we have to consider the effects of spaghettification and time dilation. As you approach the black hole's event horizon, the difference in gravitational force between your head and your feet becomes increasingly extreme. Your feet, being closer to the black hole, experience a much stronger pull than your head. This difference in gravitational force stretches you vertically, while compressing you horizontally. You would be elongated like spaghetti. This process is called spaghettification, and it would tear you apart long before you reached the event horizon, at least for smaller black holes. For supermassive black holes, the tidal forces near the event horizon are weaker, so you might make it inside relatively intact. But your problems are just beginning. But that's not all. As you approach the event horizon, time dilation comes into play. From the perspective of an outside observer, time appears to slow down for you. The closer you get, the slower time moves for you relative to them. An outside observer would never actually see you cross the event horizon. They would see you slow down, get stretched, and fade away as the light from you becomes increasingly red-shifted, shifted towards the red end of the spectrum due to the intense gravity. You would effectively be frozen in time at the event horizon, at least in their perception. But from your perspective, time would continue to pass normally, at least until you reach the singularity. What happens then? Well, that's where our understanding of physics breaks down. It's likely an unavoidable encounter with infinite density, probably resulting in your destruction. So, yeah, avoid falling into black holes. For a long time, black holes were thought to be completely inescapable, true one-way tickets to oblivion. However, in the 1970s, the brilliant physicist Stephen Hawking made a groundbreaking discovery. Black holes aren't entirely black. They emit a faint radiation, now known as Hawking radiation. Hawking radiation arises from quantum mechanics and the nature of the vacuum of space. According to quantum field theory, empty space isn't truly empty. It's filled with virtual particle-antiparticle pairs that constantly pop into and out of existence. Near the event horizon, sometimes one of these virtual particles falls into the black hole, while the other escapes. To an outside observer, it appears as if the black hole is emitting radiation. This radiation carries away energy, causing the black hole to slowly lose mass over an incredibly long period. This process is extremely slow. For a stellar mass black hole, it would take far longer than the current age of the universe to evaporate completely. Smaller black holes, however, evaporate much faster. Primordial black holes, if they exist, could be evaporating even today, potentially emitting detectable bursts of radiation. Hawking radiation has profound implications for our understanding of black holes and the fundamental laws of physics. It suggests that black holes aren't eternal, and it raises complex questions about the conservation of information, leading to the famous black hole information paradox, which is still debated by physicists today. Black holes, particularly supermassive ones, play a critical role in the evolution of galaxies. They are not just passive inhabitants. They actively shape the structure and behavior of their host galaxies. During galaxy mergers, supermassive black holes can collide and merge themselves, releasing enormous amounts of energy in the form of gravitational waves. These mergers can trigger bursts of star formation and redistribute gas and dust throughout the galaxy. Supermassive black holes can also power active galactic nuclei, AGN. When matter falls into the accretion disk around the black hole, it releases tremendous amounts of energy, making the active galactic nucleus one of the brightest objects in the universe. This energy can heat up the gas in the galaxy, suppressing star formation and regulating the galaxy's growth. Supermassive black holes can also power active galactic nuclei, AGN. When matter falls into the accretion disk around the black hole, it releases tremendous amounts of energy, making the active galactic nucleus one of the brightest objects in the universe. This energy can heat up the gas in the galaxy, suppressing star formation and regulating the galaxy's growth. The powerful jets of particles ejected from the vicinity of the black hole can also influence star formation in galaxies. These jets can either stimulate star formation by compressing gas clouds or suppress it by heating the gas and preventing it from collapsing. Furthermore, black holes can drive galactic winds and outflows, expelling gas and dust from the galaxy and regulating its overall mass and composition. These outflows can also enrich the intergalactic medium with heavy elements, influencing the formation of future generations of galaxies. Since black holes don't emit light directly, how do we detect them? Scientists use several indirect methods, relying on the effects black holes have on their surroundings. One way is to observe the motion of stars or gas clouds orbiting an unseen object. If a star is orbiting something massive but invisible, it's a strong indication of a black hole. By analyzing the star's orbit, we can determine the mass of the black hole. Another method is to look for X-ray emissions from accretion disks. As matter spirals into a black hole, it heats up to millions of degrees, emitting intense X-rays that can be detected by space-based telescopes. Gravitational lensing is another powerful tool. Black holes warp spacetime, bending the path of light. If a black hole lies between us and a distant galaxy, it can act like a lens, distorting and magnifying the galaxy's image. This allows us to infer the presence and mass of the black hole. Finally, the detection of gravitational waves has opened up a whole new window into the black hole universe. When black holes merge, they generate ripples in space-time that can be detected by observatories like LIGO and Virgo. These gravitational waves provide valuable information about the masses, spins, and distances of the merging black holes. One of the most remarkable achievements in black hole research is the Event Horizon Telescope, EHT. It doesn't work like a traditional telescope, but rather as a network of telescopes all over the world, working together to create a virtual telescope the size of the Earth. By combining data from these telescopes, the EHT can achieve an incredibly high resolution, allowing it to image the shadow of a black hole against the bright light of its accretion disk. The EHT has already captured the first-ever images of a black hole, M87 star, the supermassive black hole at the center of the Messier 87 galaxy, and Sagittarius A star, at the heart of our own Milky Way. These images confirm the predictions of Einstein's theory of general relativity and provide invaluable data for understanding the physics of black holes. It's important to note that the EHT images don't show the black hole itself, but rather the shadow of the black hole. This shadow is created by the bending of light around the black hole due to its intense gravity. The size and shape of the shadow provide a direct measure of the black hole's mass and spin. The Event Horizon Telescope is constantly being improved with the addition of new telescopes and advanced data processing techniques. In the future, a space-based EHT could provide even higher resolution images, allowing us to probe the physics of black holes in greater detail. Despite all the progress we've made in understanding black holes, many mysteries remain. They continue to challenge our understanding of physics and push the boundaries of scientific knowledge. The black hole information paradox is one of the biggest unsolved problems in theoretical physics. It arises from the conflict between quantum mechanics, which says that information cannot be destroyed, and general relativity, which suggests that information is lost when it falls into a black hole. Resolving this paradox could require a completely new understanding of gravity and quantum mechanics. The singularity at the center of a black hole is another major puzzle. Our current theories of physics break down at the singularity, where gravity is infinite and space-time is infinitely curved. To understand the singularity, we need a theory of quantum gravity that can reconcile general relativity with quantum mechanics. Candidate theories include string theory and loop quantum gravity. The formation mechanisms of supermassive black holes are still poorly understood. How did these behemoths grow to such enormous sizes in the early universe? Did they form from the collapse of massive stars, the mergers of smaller black holes, or some other exotic process? These are questions that astronomers are actively researching. Finally, black holes have captured the imagination of science fiction writers and filmmakers who have speculated about their potential for wormholes and time travel. While these ideas are highly speculative and not supported by current scientific evidence, they highlight the enduring fascination that black holes hold for the human mind. Black holes have captivated the public imagination, featuring prominently in science fiction books, movies, and TV shows. While often portrayed with a degree of artistic license, these depictions have also inspired interest in real-world black hole research. Films like Interstellar have gone to great lengths to portray black holes accurately, consulting with physicists like Kip Thorne to ensure scientific plausibility. The movie's depiction of the black hole Gargantua is based on real scientific models and simulations. Stephen Hawking's book, A Brief History of Time, played a crucial role in popularizing black holes and cosmology among a wider audience. The book explained complex scientific concepts in an accessible way, making black holes a topic of mainstream conversation. Black holes have also appeared in video games, documentaries, and other forms of media, continuing to inspire awe and wonder about the mysteries of the universe. These depictions, while sometimes exaggerated, can serve as a gateway for learning more about the real science behind black holes. The study of black holes is a rapidly evolving field, with new discoveries being made all the time. What does the future hold for black hole research? Future space-based observatories, such as LISA, will be able to detect gravitational waves from merging supermassive black holes, providing new insights into galaxy evolution and the early universe. Advanced computer simulations, including those using quantum computers, will allow us to model black holes in greater detail and test theories of quantum gravity. These simulations could help us understand the singularity and resolve the black hole information paradox. The future of black hole research depends on a combination of observational data, theoretical models, and technological advancements. By continuing to explore these fascinating objects, we can unlock new secrets about the universe and our place within it. Black holes, once relegated to the realm of science fiction, are now recognized as fundamental components of the cosmos. They are powerful engines of galactic evolution, laboratories for testing the laws of physics, and enduring sources of wonder and fascination. As we continue to explore these enigmatic objects, we can expect to make even more groundbreaking discoveries that will reshape our understanding of the universe. Thank you for joining us on this journey into the heart of a black hole. Don't forget to like this video, subscribe to our channel for more mind-blowing science content, and let us know in the comments what other cosmic mysteries you'd like us to explore. Until next time, keep looking up.